Hi, welcome to Linear Transformation Part 2. In this video, we are going to see the properties of linear transformation and types of linear transformation. Okay, now see. First, types of linear transformations. First one is, if UF and VF are two vector spaces, mapping T is from U to V, it is defined by T of alpha is equal to 0 bar. The mapping is defined as T of alpha is equal to 0 bar, where 0 bar is called vector of V. Then prove that T is a linear transformation. See here. What is U of F? U is a vector space and V is a vector space. F is a field of scalars. These two vector spaces are defined over the same field F, and T is a transformation from U to V such that T of alpha is equal to 0. T of alpha is equal to 0. That means you have taken alpha belongs to U and it is defined as T of alpha is equal to 0 bar. That means in V there exists a 0 bar which is the vector identity, that is identity element of V plus. What is V? V is an abelian group. V plus dot is a vector space. V plus dot is a vector space means V plus is a abelian group. Abelian group means there exists additive identity. That additive identity is there. Here you are taking an alpha, there are some elements in V which are mapped alpha and beta. So these are all mapped to only one element 0 bar. If you take that T, that is the mapping T of alpha, will be a linear transformation. That you have to prove. Is it clear? T of alpha is equal to 0 bar. That means you have taken some elements in U and those elements are mapped to 0 bar. If you take alpha, beta, both belongs to U such that T of alpha is equal to 0 and T of beta is also equal to 0. Now what you have to prove? T is a linear transformation. In order to prove that T is a linear transformation, you have to show that T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta. That you have to prove. In order to prove that, what we do is, because alpha and beta are in U and U plus dot is a vector space, A alpha belongs to U and B beta also belongs to U. Will you accept these two will belongs to U because U is closed with respect to scalar multiplication. A alpha plus B beta also in U. Now see, you have to consider that is T of A alpha plus B beta is equal to 0 bar. Now what you have taken? Given that UF and VF be the two vector spaces, T is a mapping from U to V defined by T of alpha is equal to 0 bar. Now you want to show that T is a linear transformation. If you want to show that T is a linear transformation, what you have to do? T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta. This you have to prove. For that, what we are doing is, we are considering T of A alpha plus B beta is equal to 0 bar. Why? Because A is in F, B is in F, A alpha plus B beta is in U. You are taking T of A alpha plus B beta is equal to 0 bar. Now this 0 bar can be written as A into 0 bar plus B into 0 bar. You can write because this 0 bar is the additive identity of V plus. So A into 0 bar. Then because alpha beta belongs to U means what you are having? T of alpha is equal to 0, T of beta is equal to 0. Like that you have taken. Okay. Now that is alpha beta belongs to U such that T of alpha is equal to T of beta is equal to 0. Now this is, since alpha is U, T of alpha is equal to 0, T of beta is equal to 0. So, A into T of alpha plus B into T of beta is equal to 0. Therefore, T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta. Now, the transformation T of alpha is equal to 0 bar. This transformation is called as 0 transformation and it is denoted by 0, and this is also called as null transformation. Okay. Now, this is the first type of transformation. See the second type, that is, suppose we have seen operator. When will you say that linear transformation is an operator? If it is defined over the same vector space. If suppose T is a linear transformation from V to V, then T is said to be linear operator. Here I is from V to V, the mapping I is from V to V, and it is defined as I of alpha is equal to alpha. The other name for this is identity operator. This is also a linear transformation. Consider I of, what is that? It is given that I is from V to V, defined by I of alpha is equal to alpha for every alpha belongs to V. Now, you have to prove that I is a linear transformation. In order to prove that I is a linear transformation, you have to consider I of A alpha plus B beta, that is A alpha plus B beta by the definition A alpha plus B beta. This is alpha is equal to I alpha, therefore A into I alpha, beta is equal to I beta, B into I beta. So, what you are able to show that I of A alpha plus B beta is A into I of alpha plus B into I of beta. Therefore, I is a linear transformation. What is I? I is a linear transformation, but it is defined from V to V. So, since the linear transformation is defined over the same set, we will say that it is an operator. I is a linear operator. The other name for this is identity operator. I is also called as identity operator. Okay. Now, see the next one. This is negative of a linear transformation. See, let UF and VF be two vector spaces. T is from U to V is a linear transformation. Then prove that the mapping minus T is defined by minus T alpha is equal to T alpha for every alpha belongs to U is a linear transformation. How is this? Minus T is from U to V, minus T alpha is equal to minus T of alpha. Now, see here, for alpha beta take in U belongs to U. So, minus T alpha minus T of alpha is equal to minus T alpha. This you have taken. Okay. Now, consider minus T of A alpha plus B beta. So, by definition it is minus T of A alpha plus B beta, is it? So, this is, you can put minus outside. This is A into T of alpha plus B into T of beta, because T is a linear transformation. Okay. So, this you can write it as minus A T alpha plus or minus B T beta. This you can write it as A into, again from the transformation, minus T of alpha plus B into minus T of beta. Okay. Now, this is minus T defined like this is a linear transformation, and it is called as negative of the linear transformation. See what you are able to see, identity operator, negative of the linear transformation, and the first one is zero transformation. Okay. Now, see we will move to the properties of linear transformations. Properties of linear transformation. Let U T is a linear transformation from U to V. Then prove that T of 0 bar is equal to 0 bar. This 0 bar is different from this 0. This 0 bar is the 0 bar of U, vector identity of U. This 0 bar is the vector identity of V. T of minus alpha is equal to minus T alpha. T of alpha minus beta is equal to T of alpha minus T of beta. And T of A1 alpha 1 plus A2 alpha 2 plus so on. A n alpha 1 is equal to A1 T alpha 1 plus A2 T alpha 2 plus so on A n T of alpha n. Okay. Now we will prove these four properties. What is given to you? T is a linear transformation from U to V. Now you have to prove that T of 0 bar is equal to 0 bar. Let alpha plus 0 bar belongs to U. Then T of alpha and T of 0 bar belongs to V, because T is a mapping from U to V. Now consider where are T of alpha and T of 0 bar in V. Consider T of alpha plus T of 0 bar. But what is T? T is a linear transformation. Therefore, T of alpha plus T of 0 bar will be equal to T of alpha plus 0 bar, because T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta. In place of A and B you are having 1, and in place of alpha and beta you are having alpha and 0. So you can write T of alpha plus 0 bar. This is just T of alpha, is it? You can write T of alpha plus 0 bar. This 0 bar is vector identity of V. Therefore, you can write. Now, if you see this T of 0 bar, T of 0 bar, T of alpha, T of 0 bar, T of alpha 0 bar. These four are the elements of V. V plus is abelian group. In an abelian group, cancellation laws will hold. So, T of alpha and T of alpha will be getting cancelled. T of 0 bar is equal to 0 bar. This is the property you have to prove. Now, second one. Now, take T of minus alpha. That you can write it as T of minus 1 into alpha. By linear property, you can write it as minus 1 into T of alpha. Therefore, it is minus T alpha. Okay. Next one. T of alpha minus beta. You can write it as T of alpha plus minus beta. That is equal to T of alpha plus T of minus beta. T of minus beta from here, it is minus T beta. T of alpha minus T of beta. Third property is over. Now, next again. For this, we use mathematical induction. What you have to prove? For n is equal to 1, the statement is induction proof. We will take n is equal to 1, the theorem is true. And for n is equal to m, it will be proved. And for n is equal to 1, it will be proved. N is equal to m, we will assume that it is true. For n is equal to m plus 1, we will prove it. Okay. Now, if n is equal to 1, take T of A1 alpha 1, that is A1 into T of alpha 1. Suppose this is true for n is equal to m. So, T of A1 alpha 1 plus A2 alpha 2 plus so on AM alpha 1 is equal to A1 into T of alpha 1 plus A2 into T of alpha 2 plus so on AM into T of alpha m, because we assumed that the equality is true for n is equal to m. Now, consider by adding one more element AM plus 1 alpha plus m, T of A1 alpha 1 plus T of A2 alpha 2 plus so on this. That is, up to this you will take as one element and this is another element. By applying the linear transformation property, this is T of A1 alpha 1 A2 alpha 2 plus so on AM alpha m. From the above condition, this will be equal to A1 into T of alpha 1 plus A2 into T of alpha 2 plus so on AM into T of alpha plus T of AM, that is AM plus 1 into T of m plus 1. Therefore, the result is true for every value of m. This is called the last one is called the linearity property of the transformation. Okay. Now, see the problems here. Is the mapping T from R3 to R defined by T of xyz is mod x comma 0 is a linear transformation. Verify whether it is a linear transformation or not. For that, what you have to take? You have to consider T of A alpha plus B beta, and you have to show that that is equal to A into T of alpha plus B into T of beta. So alpha is equal to x1 y1 z1, beta is equal to x2 y2 z2. You have taken in R3 and a comma b belongs to R. Now consider T of a alpha plus b beta, that is equal to T of a into x1 y1 z1 plus b into x2 y2 z2, that is ax1 plus bx2, ay1 plus by2, az1 plus bz2. Now according to the definition, it will be modulus of ax1 plus bx2 comma 0, that is T of a alpha plus b beta. Keep it aside as 1. Now consider a into T of alpha plus b into T of beta, a into T of x1 y1 z1 plus b into T of x2 y2 z2. By definition of the transformation, it will be a into mod x1 comma 0 plus b into mod x2 comma 0, that is ax1 plus a into mod x1 plus b into mod x2 comma 0. This is 2. From 1 and 2, you can say that T of a alpha plus b beta is not equal to a into T of alpha plus b into T of beta. Therefore, T is not a linear transformation. Is it okay? Now, see one more example. Let V be a vector space of n by n matrices over a field F. The mapping T from V to V is defined by TA is equal to AM plus MA, where A belongs to V. Then show that T is a linear transformation. What is given to you? V is a vector space of n by n matrices. M is a fixed matrix. Okay. Now let T is a mapping from V to V such that T of A is equal to AM plus MA. See here, AM is not equal to MA because matrix multiplication is not commutative. Therefore, where A belongs to V. Let AB belongs to V, A comma B belongs to F. T of AA plus BB, by transformation AA plus BB into M plus M into AA plus BB. That is, here, from here and here, if you take A into AM plus MA plus B into BM plus M. That is nothing but A into T of A plus B into T of B. Therefore, T is a linear transformation. Okay. With this, we will stop. Thank you.